Hi guys, myself I am Somrvaina Vasita. Today we are going to talk about project Simple 8-bit simulator. Let's begin with understanding what an 8-bit simulator actually. An 8-bit simulator is a software program that imitates or recreates the working of an 8-bit microprocessor. In a simple word, an 8-bit simulator is a virtual version of a tiny CPU that processes data 8 bits at a time. The main idea is that we can study and experiment with the how a real processor works, but without needing any physical hardware or a chips. It provides a completely virtual environmental to test and run assemble code and to see how CPU reacts step by step. Why building tiny simulator? An 8-bit simulator has a greater educational value. It helps beginners really understand what happens inside a computer at the most basic level. How data moves between registers, how memory is accessed, and how instructions are executed. It also be zero cost. Anyone with a computer can start experimenting with CPU Connect without needing to buy an actual microprocessor board. And most importantly, it helps building a foundation for understanding all modern communication or a computation. Once you understand 8-bit system, you can easily move on to 1632 and even though 64-bit architectures. Every CPU, whether it's a 8-bit or 64-bit, follows a structured architecture. Our simulator is a simple 8-bit CPU with all basic components working together. Key 8-bit CPU components. Let's go through them one by one. Accumulator. This is the heart of CPU where all data operations happens like addition or subtraction are performed here. Index registers X and Y. These helps in addressing memory locations or controlling loops. They were like helpers that make respective task easier. Next, program counter. This keep tracks of which instructions the CPU must execute next. Next, stack pointers. It manages the stack area in memory, which is used for temporary data storage during subroutines or function call ALU. Arithmetic logic unit. This is where all arithmetic like addition, subtraction and logical like and not operations takes place. Status flag. This stores small bit of information about the previous operation such as whether the result was 0, positive or was carry. Now all these components work together through a repeating cycle known as the switch decode execute cycle. In this cycle, the CPU fetches the next instruction from the memory. Next, it decodes what the instruction means. Next, then it executes it, performing the actual operations. Once done, it moves to the next instruction. The cycle repeats continuously, thousands and even millions of times per a second in a real CPU. Now let's also look at how memory is arranged. The memory map includes ROM, RAM, zero page, stat, general purpose RAM. First we are going to ROM, which stores the main program. Now RAM, which holds the data and variable while running. Zero page, a special fast access memory area for frequently used data. Stat, which grows downwards and is used to handle subroutines. In an 8-bit system, the address space is just 256 bytes per page. That's very small compared to the modern system, but it's enough to learn how memory and register interacts.
As Vasudhar explained about the architecture, now I am going to explain you about the instruction set. An instruction set is basically the language of the CPU. It contains all the commands the processor can understand and execute. Some of the main instructions in a 8-bit CPU are LDA. LDA loads a value into the accumulator. STA store the accumulator's value into memory. ADD and SUB performs addition and subtraction from accumulator. JMP jump to a different memory address used for loops or skipping code. BEQ branch if equal. This checks a condition and jumps into if it's true. JSR and RTS used for subroutines like calling and returning from small functions. Each of these instructions has an OP code, a hexadecimal number that represents it. For example, LDA has a OP code 0xA9. Here, let's look at the sample code. At first, the CPU loads 5 into the accumulator and then it adds 3, making the result as 8. And then it stores that 8 in memory location 80H. Then it jumps into an infinite loop, which is a common way to stop the execution. The sample code shows how instructions work together, fetch, example, and change memory or registers. Now let's see how our simulator actually runs these instructions. It follows a main cycle known as emulator loop, which consists of 4 key stages: fetch, decode, execute, update. Where in fetch, the simulator reads the next instruction from the memory location pointed by the program counter. In decode, it interrupts what that instruction means, for example, whether it's an addition, a jump, or a store. Execute, it performs that operation, updates registers, performs ALU operations, or modifies the memory. In update, it advances the program counter and updates internal times or flags. Our simulator also includes debugging tools to help us understand what's going on inside. A deassembly trace that shows the code as it executes. A register panel displaying live values of A, X, Y, PC, SP, and flags. A memory dump to view the data stored in different locations. Breakpoint and controls, so we can pass the program step through instructions and find errors like infinity loops or overflows. To conclude this project, which helped us clearly understand the fundamentals of how a CPU works, how it processes, stores, and executes instructions. It's a great foundation for anyone who wants to go into embedded systems, processor design, or low level programming. Thank you everyone for listening.